Hey everyone, and welcome to the section of reductions of the halting problem. Along this section, we will solve many reductions on the halting problem. That is, we will have a set of problems or a set of languages, and we will reduce them to the halting problem. But first of all, what is the halting problem? In theory of computation, the halting problem is the problem of determining, given a computer program and an input, whether the program will finish running, that is, if it will stop, or if it will continue to run forever. Hence, we can see this as given a word W and a Turing machine M, we need to determine whether the Turing machine M will stop with the input. So, this problem is commonly described as one of these two languages and problems. For instance, consider this language K that we see here. This language, we can see intuitively that it is the set of programs that stop with input themselves. So basically, this problem K is that for every input X that we have on our program, then the Turing machine X stops with input X. Remember that when we represent that Turing machine stops, basically it ends its execution, we represent this with an arrow pointing to the bottom. This means that this program stops. So the problem K is basically the set of programs that stop with input themselves. Given an input X and the Turing machine X with input itself, which is X, then this problem ends. Then we have other representation of the halting problem, which is basically the same idea, but now instead of only one input X, what we have here is the set of pairs program input, where X is the program and Y is the input, such that the program stops with the input. More precisely, it is the set of naturals encoding pairs of naturals X, Y, such that the machine encoded by X stops with input Y. Here is important to notice that X is the program that we have, the Turing machine X, and Y is the input on this Turing machine. And something very interesting to know is that both of them are semi-decidable problems. Both the problem K and the problem halt that we see here. That's because the halting problem is a semi-decidable problem. Now, remember the definition of a semi-decidable problem. This is something that we already covered before, but again, it is a fundamental concept. So, a problem P that is semi-decidable, this means that P belongs to the set of semi-decidable problems if, when we have the algorithm on the program on the given input and the output is yes, okay, keep in mind that when we are working with these problems we have two possible outputs, a yes or no, this is a semi-decidable problem, or any decidable problem, the answer is either yes or no. In a semi-decidable problem, if the answer is yes, then we know for sure that our program always stops. So in this sense, the Turing machine will always stop, okay? But in the case of the answer on the output being no, then our program may not stop. So it can stop, but it may not stop. So since we have the possibility that it runs forever, then this problem P is a semi-decidable problem, okay? Unlike, for instance, the decidable problems, okay? In a decidable problem, both answers, yes or no, we know for sure that will always stop, okay? The program will always stop. However, in a semi-decidable problem, then we are not sure if the answer is no, maybe it doesn't stop. All right, very well. So along this section, we will reduce many problems to the halting problem and prove whether they are semi-decidable or even undecidable with the reductions that we do. See you in the next lesson.